The morning of November 8, 1942, Richmond Shipyard Number Two, California. 4,000 workers swarmed a single assembly way like a choreographed army. Massive cranes lowered prefabricated hull sections weighing 30 tons each into position. Welding teams attacked joints from every angle, their arc flashes illuminating the pre-dawn darkness. The din was overwhelming. Metal on metal, hydraulic hisses, shouted commands echoing across 60 acres of industrial chaos. This wasn't normal shipbuilding. This was something the maritime establishment had called impossible. Henry Kaiser, the dam builder who'd never constructed a ship before Pearl Harbor, had made a promise that sounded insane. He'd build a complete 10,000-ton cargo vessel in less than a week. Not just the hull, not just the structure. A fully operational Liberty ship with functioning engines, electrical systems, steering, cargo booms, lifeboats, everything. In under 7 days, traditional shipyards had laughed at him 18 months earlier. Ships took 6 to 12 months to build because that's how long riveting required. You couldn't hammer 4 million rivets faster without compromising quality. You couldn't cure paint and sealants faster without chemistry changing. You couldn't rush sea trials without risking disaster. Shortcuts killed sailors. Everyone knew this. But Kaiser wasn't building ships the traditional way, and by November 1942, he wasn't trying to prove himself anymore. He was proving what American industrial might could accomplish when the nation's survival hung in the balance. Because 18 months earlier, Britain had been starving, and Germany had been winning. The cold Atlantic waters had become a graveyard. Every 24 hours in 1941, German U-boats were sending roughly 10 Allied merchant ships to the ocean floor. These weren't just numbers on an admiral's chart. Each vessel carried food, fuel, ammunition, and raw materials that Britain desperately needed to stay in the fight. And the math was brutally simple. If ships went down faster than new ones could be built, Britain would starve long before Hitler needed to invade. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. By March 1941, Admiral Karl Dönitz had perfected his Wolfpack tactics. Instead of solo U-boat attacks, he coordinated groups of 8 to 20 submarines that hunted convoys like predators surrounding prey. They'd surface at night when Allied radar couldn't spot them, torpedo multiple ships in minutes, then disappear beneath the waves before destroyer escorts could respond. The convoys sailed in darkness. Cargo holds packed with wheat from Canada, steel from America, oil from Trinidad, and they died in darkness too, often taking their entire crews with them. The numbers kept getting worse. In April 1941 alone, U-boats sank 168 Allied ships, totaling over 500,000 tons of shipping. In June, another 129 ships disappeared beneath the Atlantic. Britain's merchant marine was hemorrhaging faster than anyone had predicted when war broke out in 1939. Prime Minister Winston Churchill would later write that the only thing that truly frightened him during the entire war was the U-boat peril, not the Luftwaffe bombing London, not Rommel in North Africa. The silent submarines strangling Britain's supply lines. Here's what made the crisis existential. Britain imported nearly 60 million tons of supplies annually before the war. Food, raw materials, everything an island nation needed to function. By mid-1941, imports had crashed to 30 million tons. Rationing was already severe. Meat portions had shrunk to barely enough for 2 meals per week. Butter, sugar, tea, all controlled by government, coupons. Factories were running at reduced capacity because freighters carrying iron ore never made it across the ocean. The Royal Navy had fuel, but just barely. Every tanker that went down meant aircraft couldn't fly, destroyers couldn't hunt U-boats, and the entire war machine ground a little slower. The replacement problem seemed impossible to solve. Britain's historic shipyards in Belfast, Glasgow, and Newcastle were already working flat out. These facilities had been building ships the same way for generations. Teams of skilled riveters hammering metal plates together by hand, one joint at a time. A single cargo vessel took 9 months to a year to complete. The yards couldn't expand fast enough. They couldn't train riveters fast enough. They couldn't acquire steel fast enough. Traditional shipbuilding required traditional timelines, and Britain didn't have months to wait. Admiral Sir Percy Noble, Commander-in-Chief of Western Approaches Command, studied the projections in his Liverpool headquarters. German production was adding new U-boats faster than the Allies could sink them. Dönitz had started the war with 57 submarines. By autumn 1941, he had over 200 operational boats, with dozens more sliding down German slipways every month. Meanwhile, British yards were completing maybe 4 or 5 new merchant ships monthly. The equation wasn't just unbalanced, it was catastrophic. American shipyards weren't much better. The United States had entered 1941 with a peacetime merchant marine and peacetime production schedules. West Coast facilities were small operations, building a handful of specialized vessels per year. East Coast yards focused on warships for the Navy. Nobody had the capacity to suddenly produce hundreds of merchant ships. And even if they did, conventional wisdom said you simply couldn't rush shipbuilding without compromising quality and safety. Then President Roosevelt made a promise that sounded insane. On January 6, 1941, Roosevelt stood before Congress and announced America would become the arsenal of democracy. The British needed merchant ships immediately, and Roosevelt committed to building 200 standardized cargo vessels as fast as humanly possible. The Maritime Commission nodded and smiled for the cameras. Behind closed doors, they calculated the brutal reality. Traditional shipbuilding methods would deliver those 200 ships sometime around 1945. Maybe, if everything went perfectly. Understanding why requires looking at how ships had been built for the past century. Traditional construction was an art form mastered by skilled craftsmen over years of apprenticeship. The process started with laying the keel, then building up the frame with massive steel ribs. Once the skeleton stood complete, workers attached steel plates to the frame using rivets. Thousands upon thousands of rivets. A typical cargo ship required approximately 4 million individual rivets hammered into place by hand. The riveting process itself was almost medieval in its demands. Teams worked in pairs or threes. The heater boy heated rivets in a portable forge until they glowed cherry red. He'd toss the scalding rivet to the catcher who'd snag it from the air with special tongs and jam it through aligned holes in the steel plates. Then the bucker pressed against the rivet's rounded head with a heavy iron bar, while the riveter on the opposite side hammered the protruding shank with a pneumatic gun, mushrooming it flat. The noise was deafening, the heat unbearable, the pace exhausting. A good riveting crew could place maybe 300 rivets per shift. Do the math. 4 million rivets divided by 300 per day meant over 13,000 working days for the riveting alone. Even with multiple crews working simultaneously on different sections, the riveting phase consumed months. And that's assuming you had enough skilled riveters, which America absolutely did not. Learning to rivet properly took years. The heater had to judge temperature by color. The catcher needed reflexes and precision. The bucker required strength and endurance. The riveter needed to control that pneumatic hammer with surgical accuracy or risk creating weak joints that would fail at sea. Beyond riveting, every other aspect of traditional shipbuilding demanded specialized expertise. Shipwrights planned the construction sequence, ensuring weight distribution and structural integrity. Marine engineers installed steam engines and boiler systems. Pipe fitters routed miles of plumbing for ballast, fuel, and fire suppression. Electricians wired lighting and communication systems. Each trade had its own apprenticeship path, its own union, its own closely guarded knowledge. You couldn't just grab random workers off the street and tell them to build ships. The maritime unions would riot, and the ships would sink. The Maritime Commission surveyed America's existing shipyards. Todd Shipyards in New York, Bethlehem Steel's facility in Baltimore, Newport News in Virginia. All excellent operations, all running near capacity, all committed to building warships for the Navy. These yards could maybe possibly squeeze out an extra merchant vessel here and there if you threw money at the problem. But 200 ships on an accelerated schedule? The Maritime Commission's chief engineer calculated it would require building at least 6 entirely new shipyards from scratch, training thousands of workers in traditional techniques, and somehow acquiring enough steel when every industry in America was competing for the same limited supply. And even if you solved all those problems, the timeline remained fixed. A ship took 6 to 12 months to build because that's how long the process required. You couldn't hammer rivets faster without compromising quality. You couldn't cure paint and sealants faster without chemistry changing. You couldn't rush sea trials without risking disaster. Traditional shipbuilding had perfected itself over generations specifically because shortcuts killed sailors. The establishment knew this in their bones. When some California construction contractor named Henry Kaiser started making noise about building merchant ships, the maritime community dismissed him as a crank. Henry John Kaiser had never set foot on a ship deck as a builder. His expertise came from dirt, concrete, and steel spanning canyons. He'd made his fortune constructing roads in California and Washington, then cemented his reputation by helping build the Hoover Dam and the Grand Coulee Dam. He understood large-scale industrial projects, tight deadlines, and innovative construction techniques. What he didn't understand, according to every shipbuilder on both coasts, was that ships float in water and require entirely different engineering principles than bridges anchored to bedrock. Kaiser didn't care about their skepticism. He saw the shipbuilding crisis through a contractor's eyes, not a shipwright's. When the Maritime Commission issued its desperate call for new production capacity in 1940, Kaiser submitted a proposal that made traditional shipbuilders laugh out loud. He'd build an entirely new shipyard in Richmond, California, hire workers with zero maritime experience, and deliver finished cargo vessels in 60 to 90 days using mass production techniques borrowed from the automotive industry. The old guard called it fantasy. The Maritime Commission, drowning in impossible demands, decided to give the crazy contractor a chance. Kaiser's background actually made him perfect for this moment. During the Hoover Dam project, he'd coordinated 6 different construction companies, orchestrated deliveries of millions of tons of concrete, and finished the job 2 years ahead of schedule. He'd done it by treating construction like manufacturing. Prefabricate components off-site, standardized designs to eliminate custom work. Train specialized crews to repeat specific tasks efficiently, work around the clock in multiple shifts. These weren't shipbuilding principles because they'd never been applied to shipbuilding. Kaiser intended to change that. The British had already designed the perfect vessel for his experiment. In December 1940, the British merchant fleet was so desperate they'd ordered 60 cargo ships from American yards based on a steamer design from 1939. The ship was deliberately simple, 441 feet long, a basic reciprocating steam engine, 5 cargo holds, top speed of 11 knots. Nothing fancy, nothing experimental, just a floating box that could carry 10,000 tons of cargo across the Atlantic. The British called them Empire ships. The Americans would call them Liberty ships, after Roosevelt declared 1941 the year of liberty for oppressed nations. Kaiser studied the Liberty ship blueprints and saw something naval architects had missed. The design wasn't a ship. It was a giant 3-dimensional jigsaw puzzle that could be assembled from prefabricated sections. Instead of building the vessel from keel up in one continuous process, why not construct major components separately in dedicated workshops, then crane them into position and join them together? An automotive assembly line built cars from subassemblies. Why couldn't a shipyard build ships the same way? The traditional approach built ships from the bottom up because riveting required access from both sides of the steel plates. You couldn't prefabricate a complete bow section in a workshop because once it was fully riveted together, you couldn't reach interior joints that still needed connecting during final assembly. But Kaiser's team had been watching a different construction method gaining traction in industrial applications: welding. Instead of hammering rivets, you could fuse steel plates together, using an electric arc that melted the metal edges and joined them permanently. Welded joints didn't need access from both sides. A skilled welder could work from one direction and create a seal as strong as a riveted connection. Welding changed everything. If you could weld instead of rivet, you could prefabricate entire sections complete with interior framing, then weld those sections together during final assembly. A team could build the bow in one workshop, the stern in another, complete deck sections in a third area, all simultaneously. Instead of 9 months of sequential construction, you'd have weeks of parallel production followed by rapid assembly. The ship wouldn't take less time to build. It would take less time because you'd be building multiple ships at once in component form, then assembling them in sequence. The Maritime Commission awarded Kaiser a contract to build 30 Liberty ships with an option for more if he delivered. Traditional shipbuilders placed bets on when the amateur would fail spectacularly. Kaiser's first Richmond shipyard broke ground in January 1941 on a muddy waterfront lot that had been farmland 6 months earlier. While construction crews poured concrete foundations for workshops and assemblyways, Kaiser's engineers tackled the welding challenge. Electric arc welding existed, but maritime tradition insisted it wasn't suitable for ocean-going vessels. The Navy prohibited welding on warship hulls. Lloyd's of London, the insurance authority for merchant shipping, expressed serious reservations. Every maritime engineer knew riveted joints had proven themselves for 80 years. Welding was experimental, unproven, potentially catastrophic. The engineers ignored tradition and examined physics. A riveted joint worked through mechanical compression. The rivet shank filled a hole drilled through overlapping steel plates, and hammering the ends created clamping force that held everything together through friction. Strong enough for most conditions, but riveted joints had inherent weaknesses. Each rivet hole removed metal, creating thousands of potential stress concentration points. The plates could still shift slightly under load. Riveted holes leaked until the steel swelled from seawater exposure, and even then they continued seeping at the seams. Welding created a fundamentally different connection. The electric arc heated steel to roughly 3,600 degrees Fahrenheit, melting the plate edges along with a filler rod. When the molten metal cooled, you didn't have 2 plates held together by a fastener. You had one continuous piece of steel. The joint was as strong as the surrounding plate because metallurgically it was the same material. No holes weakening the structure, no gaps allowing water infiltration, no mechanical parts to corrode or work loose. A properly executed weld was simply better engineering. The training problem seemed insurmountable until Kaiser reframed it. You couldn't train a riveter in less than 2 years because the job required 4 coordinated specialists working in brutal conditions. But welding? One person with an electrode holder and a clear view of the joint could lay a perfect bead after 6 weeks of practice. The skill ceiling was high, certainly, but the skill floor was remarkably low. Anyone with steady hands and good eyesight could learn basic welding. Kaiser's training program didn't need to produce master craftsmen. It needed to produce competent operators who could follow procedures and maintain consistent quality. Richmond Shipyard Number One opened its welding school in April 1941. The first classes enrolled shipyard workers transitioning from traditional trades, but Kaiser quickly expanded recruitment. Newspaper advertisements across California announced that no experience was necessary. The shipyard would teach you a valuable trade, pay you while learning, then employ you at wages comparable to skilled craftsmen. Farmers facing drought drove to Richmond. Workers from depression-shuttered factories applied by the hundreds. Women showed up despite Maritime Commission officials insisting welding was too dangerous and physically demanding for female workers. Kaiser hired them anyway. The training program compressed years of apprenticeship into concentrated instruction. Week 1 covered safety, equipment operation, and basic metallurgy. Students learned to strike an arc, maintain proper electrode angle, and control travel speed. Week 2 introduced different joint types and positions. Flat welding on a horizontal surface was easiest. Vertical welding required fighting gravity. Overhead welding rained molten metal on your shoulders. By week 4, trainees practiced on actual ship sections, laying beads that inspectors examined with dye-penetrant tests and X-rays. Students who consistently produced acceptable welds graduated to the shipyard floor. Those who struggled repeated sections until they succeeded or washed out. The difference in labor requirements was staggering. A riveted Liberty ship required 120 riveters working 10 months. A welded Liberty ship required roughly 60 welders working 6 weeks on final assembly, plus additional welders working simultaneously on prefabricated sections. Kaiser replaced 4 million rivets with approximately 30 miles of welded seams. Instead of hammering fasteners one at a time, welders fused continuous joints at speeds approaching 12 inches per minute. The math finally worked. By August 1941, Richmond Shipyard Number One had transformed from muddy wasteland into an industrial complex covering over 60 acres. But it looked nothing like traditional shipyards with their massive building slips and towering cranes clustered around a single vessel. Kaiser had designed something entirely different. A factory floor for ship manufacturing. 7 massive assembly ways ran parallel to the Gravik waterfront where finished ships would launch. Behind them stretched dozens of prefabrication workshops organized by component type. Building 1 fabricated bow sections. Building 2 handled sterns. Building 3 produced deck panels. Building 4 assembled deckhouse structures. Each workshop operated like a dedicated production line feeding the final assembly ways. The prefabrication system worked like this. Engineers divided the Liberty ship design into roughly 250 major subassemblies. Each subassembly was small enough to be built in a workshop and transported by crane, but large enough to minimize final assembly time. A complete bow section might weigh 30 tons and include the outer hull plates, interior framing, bulkheads, and piping already installed. Workers built these sections on specially designed jigs that held all the components in precise alignment while welders joined them. The jigs were reusable patterns identical for every ship, eliminating the custom fitting that consumed weeks in traditional construction. The workforce assembling these sections looked nothing like a traditional shipyard crew. By October 1941, Richmond employed over 15,000 workers. 60% had never worked in heavy industry before. The yard hired Edgar Kaiser, Henry's son, specifically to manage personnel and training. Edgar walked the yard floor and saw former school teachers learning to operate overhead cranes. Dust Bowl refugees from Oklahoma operated cutting torches. Housewives from Oakland welded bulkheads. Retirees who'd spent careers farming installed piping systems. The oldest welder was 67. The youngest was 19. Women comprised roughly 30% of the workforce by 1942, shattering every assumption about industrial capability. Wendy the welder became a recruiting poster icon. But thousands of real women performed every job in the yard except the heaviest lifting. They welded as accurately as men. They operated cranes with precision. They read blueprints, performed inspections, and supervised construction crews. The yard paid equal wages for equal work because production quotas mattered more than gender politics. If you could do the job, you got the job and the paycheck. The yard operated 24 hours daily in 3 8-hour shifts. First shift started at 7 in the morning, second shift began at 3 in the afternoon. Graveyard shift ran from 11 at night until 7. Workers arriving for each shift found their assigned stations already set up with materials and equipment. Prefabrication workshops maintained continuous production, feeding completed sections to the assembly ways where they'd be installed during that shift's allocation. The night crew picked up exactly where the day crew stopped, following progress charts updated hourly. Kaiser organized work teams around specific repetitive tasks rather than traditional trades. One team did nothing but weld, longitudinal seams on hull sections. Another team specialized in connecting bulkheads to frames. A third team exclusively installed piping bundles. This specialization meant workers achieved expertise quickly in their narrow domain, rather than spending years learning an entire trade. A welder who spent 8 hours daily welding the same joint configuration in the same position became extraordinarily efficient at that specific operation. Traditional shipwrights called it de-skilling. Kaiser called it productivity. The assembly ways operated on a schedule synchronized across all 7 positions. When Ship 1 finished and launched, Ship 2 moved forward 1 position. Ship 3 advanced to position 2, and so on. A new keel was laid in position 7 the same day. Like automobiles moving down an assembly line, ships progressed through stations where specific work happened at each position. Early stations installed the bottom hull sections and engine room components. Middle stations added deck structures and superstructure. Final stations completed outfitting with equipment, piping, wiring, and paint. Every ship spent approximately the same time at each station, creating predictable workflow and resource allocation. The first Liberty ship completed at Richmond, the SS Patrick Henry, launched on September 27, 1941, after roughly 150 days of construction. Traditional shipbuilders nodded knowingly. "See," they said, "Kaiser's revolutionary methods delivered a ship in 5 months instead of 9. Impressive for an amateur, but hardly the miracle he'd promised." They stopped talking 3 months later when Richmond launched its next ship after 90 days of construction, then another after 75 days. By spring 1942, Richmond was completing ships every 40 days, then every 30 days, then faster. What the skeptics failed to understand was that Kaiser's system needed time to optimize. Those early ships taught the workforce how prefabrication worked, revealed bottlenecks in the process, and proved which innovations succeeded. By the time Richmond Shipyard Number Two opened in January 1942, Kaiser's team had refined their methods into a genuinely revolutionary system. The second yard incorporated lessons from the first with better workshop layouts, improved jig designs, and streamlined material flow. Production times collapsed. Competition between Kaiser's yards intensified throughout 1942. Richmond Shipyard Number One completed a Liberty ship in 41 days. Richmond Number Two countered with 37 days. Number One responded with 33 days. Workers checked production boards obsessively, tracking which yard held the record. Management encouraged the rivalry, offering bonuses to teams that beat previous records. The competition wasn't just internal. Kaiser's operations competed with Oregon Shipbuilding in Portland, another Kaiser-managed facility, and with other shipbuilders up and down the West Coast. The records fell with dizzying speed through autumn 1942. Oregon Shipbuilding completed a Liberty ship in 30 days. Richmond Number Two answered with 27 days. In early November, Kaiser announced that Richmond Number Two would attempt something unprecedented, building a complete Liberty ship in under 1 week to demonstrate American industrial might for a visiting delegation of Allied officials and to raise money for war bonds. The Maritime Commission thought he'd lost his mind. A week to build a ship? Impossible. Kaiser chose the SS Robert E. Peary for the record attempt, named after the Arctic explorer. Richmond Number Two had been preparing for weeks, stockpiling prefabricated sections, training crews on rapid assembly procedures, and choreographing every movement like a military operation. The keel touched down on the assembly way at 12:01 a.m. on Sunday, November 8, 1942. Over 4,000 workers swarmed the site across all 3 shifts, working with surgical precision. Massive cranes lowered prefabricated hull sections into position every few hours. Welding teams swarmed each joint, working simultaneously on dozens of connections. The bottom hull took shape in 16 hours. Engine room sections dropped into place on Monday morning. By Monday night, the deck was going on. Tuesday brought the superstructure, deck houses, and masts. Wednesday focused on outfitting, miles of piping, electrical systems, ventilation equipment, cargo booms, lifeboats, navigational equipment. Thursday morning, painters applied the final coat while engineers conducted system tests. Thursday, November 12th, at 3:30 p.m. Exactly 4 days, 15 hours, and 29 minutes after the keel was laid, the SS Robert E. Peary slid down the ways into San Francisco Bay, fully operational. The ship had functioning engines, loaded fuel tanks, working steering, complete electrical systems, and it passed every safety inspection. Photographers captured the moment, newsreel cameras rolled, the crowd of workers and officials erupted in cheers. Kaiser had built a 10,000-ton cargo ship in less time than it took traditional yards to finish the riveting. The record was technically a stunt requiring extraordinary preparation and resources concentrated on one vessel, but it proved Kaiser's methods worked. By the end of 1942, America's new shipyards were averaging 42 hours between Liberty ship launches across all facilities. Not 42 hours to build one ship, but a new ship sliding into the water every 42 hours, because multiple ships were always under construction simultaneously at various stages. The production numbers tell one story. By the end of 1943, American shipyards delivered over 1,200 Liberty ships. Kaiser's yards alone produced over 750 vessels. The United States was launching 3 ships daily, overwhelming German submarine production by a factor of 10 to 1. Admiral Dönitz watched his wolf packs sink fewer ships each month, while Allied convoys grew larger and more numerous. By mid-1943, convoys crossing the Atlantic delivered 11 million tons of cargo monthly, more than replacing losses. The U-boat menace hadn't disappeared, but the stranglehold had broken. Britain received food, fuel, ammunition, and equipment in quantities that made invasion planning possible. Liberty ships were winning the Battle of the Atlantic. Then ships started breaking in half. The first catastrophic failure happened in January 1943. The SS Schenectady, barely 3 months old, sat docked in Portland Harbor in calm water when crew members heard a sound like a rifle shot. A crack appeared in the deck, raced along the hull, and split the ship completely in two just after the bridge. The stern section sank. The bow settled onto the harbour bottom. The ship hadn't hit anything. No explosion, no storm damage. It simply fractured while sitting peacefully at the dock. Engineers initially dismissed it as a freak accident, possibly bad steel or improper welding. Then the SS John P. Gaines broke in half near Seattle. The SS Esso Manhattan cracked while sailing in moderate seas. By March 1943, over 20 Liberty ships had experienced serious structural failures. Some developed cracks that could be repaired. Others broke catastrophically. The Maritime Commission couldn't ignore it anymore. Something was fundamentally wrong with welded ship construction. The investigation revealed a phenomenon called brittle fracture that naval architects had never encountered at this scale. Steel normally behaves in a ductile manner, meaning it deforms and bends before breaking. You can see this with a paperclip. Bend it back and forth and it gradually work hardens before finally snapping. But under certain conditions, steel transforms from ductile to brittle, shattering like glass with almost no warning. The conditions that trigger this transformation are low temperatures, high stress concentrations, and specific metallurgical factors. Liberty ships sailed in North Atlantic waters where temperatures dropped below freezing. The steel plates used in construction came from mills producing to minimum specifications for cost efficiency. Some batches had high sulfur content which reduced ductility. The ships operated with heavy cargo loads that created constant stress on the hull, but the critical factor was welding itself. A welded seam created a continuous stress path across the entire structure. In a riveted ship, cracks forming at one rivet couldn't easily propagate because the next rivet hole interrupted the stress field. In a welded ship, once a crack started, nothing stopped it from racing along the entire weld seam. The problem intensified at corners and cutouts. Every hatch opening, doorway, and window created a stress concentration point where forces focused. Traditional ships had rounded corners and gradual transitions that distributed stress. Liberty ships built for speed and simplicity used square hatches with sharp 90-degree corners. Engineers call these stress risers. When brittle steel under tension encountered a stress riser, catastrophic fracture could initiate from a welding flaw smaller than a pinhead. Constance Tipper, a British metallurgist at Cambridge University, led the scientific investigation. Her research demonstrated that the transition from ductile to brittle behavior occurred at specific temperatures depending on steel composition. Lower quality steel transitioned at higher temperatures. Many Liberty ship plates became brittle at temperatures commonly encountered in winter Atlantic crossings. She also proved that welding altered the steel's grain structure in the heat-affected zone next to the weld, creating regions more susceptible to brittle fracture. The Maritime Commission faced a nightmare scenario. Over 2,000 Liberty ships were either completed or under construction, using identical designs and methods. The fix came faster than anyone expected, because Kaiser and the Maritime Commission couldn't afford to stop production. Engineers retrofitted existing ships with crack arresters, steel straps riveted across vulnerable areas to stop fracture propagation. Naval architects redesigned hatch corners, replacing sharp angles with rounded transitions that distributed stress smoothly. The Maritime Commission mandated higher quality steel with lower sulfur content and better low-temperature properties. Most importantly, welders received additional training in proper technique, focusing on eliminating the tiny flaws that could initiate cracks. The redesigned Liberty ships, designated EC2SC1 in official documentation, incorporated these fixes from the keel up: rounded hatch corners, crack arrestor plates built into the structure, better steel specifications, more rigorous welding inspection using X-ray and ultrasonic testing. The modifications added roughly 3 days to construction time and increased costs by about 8%, but ships stopped breaking. By late 1943, catastrophic fractures essentially ceased while production barely slowed. The lessons learned from failure made welded construction stronger than riveting ever was. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. By the time Germany surrendered in May 1945, American shipyards had delivered 2,710 Liberty ships. Kaiser's operations built over 1,400 of them. The total construction time for the entire program? Roughly 4 years to build more tonnage than existed in the entire pre-war American merchant marine. The ships carried 7 million tons of cargo to European and Pacific theatres. They transported tanks to North Africa, ammunition to Normandy, and food to liberated populations. 72 Liberty ships were lost to enemy action, weather, or accidents. The rest sailed through the war and continued serving for decades afterward. The revolution Kaiser unleashed didn't end with victory. Traditional shipbuilding died in those California and Oregon yards. After the war, no major shipyard returned to riveting. Welding became the universal standard for ship construction worldwide. The techniques developed under wartime pressure, refined through catastrophic failure and engineering analysis, established the foundation for modern maritime engineering. Today's container ships, oil tankers, and naval vessels all descend directly from Kaiser's welded Liberty ships. The prefabrication methods proved even more revolutionary. Modern shipyards from South Korea to Finland build ships exactly as Kaiser did, construct massive sections in specialized workshops, then assemble them rapidly at the waterfront. The vocabulary changed. They call them modules now instead of sub-assemblies, but the principle remains identical. Contemporary shipbuilders produce vessels in months rather than years because Kaiser proved that parallel production beats sequential construction every time. The human impact matched the technical revolution. Over 1 million Americans worked in wartime shipyards, learning industrial trades that supported them through decades of post-war prosperity. Women who welded Liberty ships became machinists, electricians, and factory supervisors. Men who operated cranes built the suburban homes and urban infrastructure of 1950s America. The shipyard training programs demonstrated that ordinary people could master advanced technical skills quickly if given proper instruction and opportunity. That lesson influenced everything from the GI Bill to community college systems. Kaiser himself leveraged wartime success into a business, empire. Kaiser Steel, Kaiser Aluminum, Kaiser Permanente Healthcare. His belief that industrial efficiency could solve social problems shaped mid-century American capitalism. Critics noted he'd become wealthy building ships with government contracts and subsidized steel. Supporters pointed out he'd delivered exactly what the nation needed when traditional experts said it couldn't be done. The Liberty ships themselves sailed for decades after the war. Some carried cargo commercially until the 1970s. Two remain operational today as museum ships. The SS Jeremiah O'Brien, permanently moored in San Francisco, still has its original reciprocating steam engine and can sail under its own power. The SS John W. Brown serves as a living museum in Baltimore. But the real story of the Liberty ships isn't just about engineering innovation or industrial efficiency. It's about what happens when a nation faces existential threat and chooses to reimagine what's possible. In 1941, Britain was losing the Battle of the Atlantic. U-boats were sinking ships faster than they could be replaced. The maritime establishment insisted shipbuilding couldn't be accelerated without compromising safety. Traditional methods had evolved over generations specifically because shortcuts killed sailors. Every expert knew you couldn't rush the process. They were wrong. Kaiser proved you could rush the process if you changed the process. You could replace skilled craftsmen with trained operators if you simplified the tasks. You could compress years of construction into weeks if you built components in parallel instead of sequentially. You could use welding instead of riveting if you understood the metallurgy and trained people properly. The skeptics who dismissed Kaiser in 1940 had legitimate concerns. Welding was experimental. Prefabrication was unproven. Mass production techniques worked for automobiles, not ships. Amateur shipbuilders would create floating coffins that would kill their crews. And they were partially right. The brittle fracture crisis showed that innovation comes with risk. Ships did break in half. The Maritime Commission did face a nightmare scenario where their revolutionary construction methods appeared fundamentally flawed. But here's what the skeptics missed. When Liberty ships started breaking, Kaiser didn't abandon his methods. He fixed them. Engineers identified the problem, metallurgists explained the science, naval architects redesigned the weak points, and workers implemented the solutions. Within months, the fractures stopped. The ships kept launching. The production continued. That's the real lesson of the Liberty ships. Not that innovation is risk-free, but that problems can be solved if you're committed to solving them. Not that traditional expertise is worthless, but that expertise must evolve when circumstances demand it. Not that shortcuts are acceptable, but that what looks like a shortcut might actually be a better way. Consider the mathematics of the Atlantic War. In 1941, Germany was building U-boats faster than the Allies could sink them and sinking merchant ships faster than the Allies could build them. Britain needed to reverse both equations simultaneously. They needed to destroy more U-boats and build more merchant ships. The U-boat problem required technological innovation in radar, sonar, and cryptography. The shipbuilding problem required industrial innovation in manufacturing. Kaiser provided the industrial solution. His methods weren't perfect. The brittle fracture crisis demonstrated that. But his methods were good enough and fast enough to tip the balance. By mid-1943, American shipyards were launching Liberty ships faster than Germany could sink them. The equation that had been killing Britain reversed. Imports increased. Rationing eased. The build-up for D-Day became possible. The ugly ducklings, as President Roosevelt called them, weren't beautiful. They weren't fast. They weren't elegant. A Liberty ship could barely make 11 knots in calm seas. If the Atlantic currents ran against them, they sometimes couldn't make forward progress at all. Their defensive capabilities were minimal. A 3-inch bow gun, a 5-inch stern gun, and some anti-aircraft weaponry made them vulnerable to everything Germany threw at them. But they floated. They carried cargo, and there were thousands of them. That's what won the Battle of the Atlantic. Not superior technology, not brilliant tactics, not heroic sacrifice, though all those things mattered. What won was arithmetic, Germany couldn't sink ships faster than America could build them. The wolf packs that had terrorized the Atlantic in 1941 found themselves overwhelmed by sheer numbers in 1943. Dönitz understood this. His memoirs, written after the war, describe the moment he realized Germany had lost the Atlantic battle. It wasn't a specific defeat. It wasn't a new Allied weapon. It was the realization that American industrial capacity had made the submarine campaign mathematically impossible. No matter how many ships his U-boats sank, more kept coming. The convoys kept getting larger. The supplies kept flowing. The Liberty ship program represented American industrial warfare at its most effective. Simple enough to build quickly, adequate enough to be combat effective, available in sufficient numbers to overwhelm the enemy. These weren't the best ships. They were good enough ships built fast enough and in large enough quantities to make best ships irrelevant. That distinction matters. Military history often focuses on superlative weapons. The fastest fighter, the heaviest tank, the most accurate bomber. But wars aren't won by the best individual weapons. They're won by the side that can field adequate weapons in overwhelming numbers, while maintaining supply lines and replacing losses. The Sherman tank wasn't the best tank of World War II. German Panthers and Tigers had better armor and bigger guns. But America built 50,000 Shermans. Germany built 6,000 Panthers and 1,300 Tigers. The arithmetic favored adequacy in quantity over superiority in quality. The Liberty ship followed the same logic. Traditional shipbuilders could have built better ships, given enough time. Ships with more speed, better seakeeping, superior construction. But those ships would have taken a year each to build. Britain would have starved before the first dozen launched. Kaiser built adequate ships in 6 weeks. Britain survived. Germany lost. There's a deeper lesson here about innovation and crisis. Peacetime innovation tends to be incremental. Shipbuilders in the 1930s improved construction techniques gradually, refining methods that had worked for decades. Riveting got slightly more efficient. Steel got marginally stronger. Designs became incrementally better. This gradual improvement works fine when time allows for iteration and testing. Crisis forces revolutionary change. When Britain faced starvation and America faced the possibility of losing its most important ally, incremental improvement became irrelevant. The nation needed ships immediately, not better ships eventually. That urgency created space for someone like Kaiser to challenge every assumption about shipbuilding. Would Kaiser's methods have been adopted in peacetime? Almost certainly not. The maritime unions would have fought prefabrication as de-skilling. Naval architects would have insisted on more testing before accepting welded construction. The Navy would have demanded proof that ships built by amateurs could survive at sea. Traditional shipyards would have lobbied against competition from industrialists with no maritime experience. But this wasn't peacetime. This was existential crisis. Britain was starving. Germany was winning. The old ways weren't working fast enough. Roosevelt gave Kaiser a chance because Roosevelt understood that losing slowly with traditional methods was still losing. The Liberty ship program also reveals something about American industrial culture in the 1940s. The willingness to hire anyone who could do the job regardless of experience, gender, or background wasn't pure idealism. It was necessity. The nation needed 1 million shipyard workers and didn't have 1 million trained shipwrights, so Kaiser hired farmers and waitresses and housewives and taught them to weld. He hired women despite objections from officials who insisted welding was too physically demanding for females. He paid equal wages because he needed the labor more than he needed to preserve social hierarchies. This wasn't social revolution. This was pragmatism. The war forced American industry to discover that its assumptions about who could do skilled work were wrong. Women could weld as accurately as men. Farmers could learn to operate cranes. Teenagers could read blueprints. The skills that maritime unions had insisted required years of apprenticeship could be taught in weeks if you broke them into specific tasks and provided proper training. After the war, many of these workers returned to traditional gender roles. The women who'd built Liberty ships were expected to return to domestic duties. But the experience changed the nation's understanding of human capability. The GI Bill's emphasis on training and education, the expansion of community colleges, the growth of technical schools, all reflected lessons learned from wartime training programs. If you could teach a housewife to weld a ship in 6 weeks, maybe you could teach veterans skilled trades that would support middle-class lives. The Liberty ships also demonstrated something about American manufacturing philosophy that would dominate the post-war economy. The emphasis on mass production, standardization, and interchangeable parts wasn't new. Henry Ford had pioneered these techniques in automobile manufacturing decades earlier. But applying these principles to something as complex as ocean-going vessels was revolutionary. Traditional shipbuilding treated each vessel as a unique creation. Even ships built to the same design had variations because skilled craftsmen adapted to specific conditions during construction. This craftsmanship approach produced excellent ships but made production slow and replacement difficult. Kaiser's approach treated ships as manufactured products. Every Liberty ship was identical. Parts were interchangeable. A propeller shaft built in one factory would fit any Liberty ship. An engine manufactured by one company would work in any engine room. This standardization meant repairs could use parts from any supplier. Damaged ships could be fixed quickly using stockpiled components. This manufacturing philosophy would define American industry for decades. Consumer products, military equipment, even housing would follow similar principles. Standardized designs, interchangeable parts, mass production. The post-war suburban boom relied on prefabricated housing components assembled on site, exactly like Kaiser's Liberty ships. The interstate highway system used standardized bridge designs. The military standardized everything from rifle ammunition to aircraft engines. Whether this standardization represents progress or loss depends on your perspective. Traditional craftsmen mourned the loss of individual expertise and pride in unique creations. Industrial engineers celebrated efficiency and scale. Both perspectives have merit. What's undeniable is that standardization and mass production won World War II. Germany produced better tanks and better submarines. America produced more tanks and more submarines and more merchant ships. Quantity crushed quality. The final accounting is straightforward. 18 American shipyards built 2,710 Liberty ships between 1941 and 1945. That's an average of 3 ships every 2 days for 4 years. The ships carried approximately 2/3 of all cargo transported by the United States during the war. They delivered the tanks that fought in North Africa, the ammunition used at Normandy, the food that kept Britain fighting, the fuel that kept aircraft flying, the equipment that rebuilt Europe. 200 were sunk by enemy action. Most survived the war. Some continued serving commercially for decades. A handful were converted to other uses. Many were scrapped when they became obsolete. 2 remain operational as museums, testament to what American industry accomplished when the nation's survival demanded it. But the numbers don't capture the human experience. The welders who'd been waitresses, the crane operators who'd been farmers, the supervisors who'd been housewives, the men too old for military service who found purpose building ships, the teenagers learning trades that would support them for life, the communities that sprang up around shipyards, transforming farmland into industrial cities almost overnight. Richmond, California, grew from a population of 23,000 in 1940 to nearly 100,000 by 1943. Housing couldn't keep up. Workers lived in temporary barracks, trailers, converted warehouses. The city built schools for workers' children, hospitals for injuries, daycare centers so mothers could work shipyard shifts. The infrastructure required to support 24-hour shipbuilding operations transformed the entire region. These boomtowns collapsed when the war ended. Kaiser closed his Richmond shipyards in 1945. Tens of thousands of workers lost their jobs within months. The temporary communities that had housed them emptied. The infrastructure built for war production became surplus. Many workers moved on to other opportunities. Some stayed, finding new employment as the region transitioned to peacetime. Economy. The cities that had exploded in growth contracted almost as quickly, but the experience stayed with the people who lived it. Veterans of the shipyards remembered it as a time when their work mattered absolutely, when the ships they built kept Britain alive and made victory possible, when their contributions, regardless of whether they wore uniforms, helped defeat fascism. That sense of purpose, of being part of something larger than themselves, shaped their understanding of American potential. Stand on the deck of the SS Jeremiah O'Brien today. The ship is 79 years old. Its hull is welded steel, built by workers, most of whom had never seen a ship before Pearl Harbor. Its engine is the same reciprocating steam engine installed in 1943. Volunteers maintain it in working condition. The ship still sails occasionally, a floating reminder of what a nation accomplished when survival demanded innovation. The critics who laughed at Kaiser in 1941 called his ships ugly ducklings. President Roosevelt embraced the nickname. The ships were ugly. Their design was obsolete before they launched. Their speed was inadequate. Their construction was rushed. Their crews called them makeshift contraptions, held together by welding and hope. But those ugly ducklings kept Britain alive. They transported the armies that liberated Europe. They carried the supplies that defeated Germany. They proved that adequate weapons built quickly and in quantity could overwhelm superior weapons built slowly and in limited numbers. The 2,710 Liberty ships didn't win World War II alone, but without them, the Allies couldn't have won at all. That's the measure of their importance. Not that they were the best ships, but that they were the ships that made victory possible. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.